And when you're not speaking?
Yes? Okay, very good. We are going to start our morning sessions. This first, is it? Can I start? The first speaker is Monica Tertaltarelli, who is going to talk about rare decays and tests of lepton flavor universality. So, when there are 10 minutes to go, I will tell you, okay?
And the control side. Okay, so it's really a pleasure to be here again in person after all this time. And so thanks to the organizers to have given me such an opportunity. And today I will cover the subject of rare decays and tests of lepton flavor universality in B quark flavor physics at Lhcb. And actually, I had a short chat with Matthias Neubert there, and he was saying this is a workshop, this is not a school. But in fact, I read it is in institute, you said. It's school and institute. So mine will be a lecture for a school. Okay, so let me start by introducing the subject. Why is it interesting to study flavor? Well, we have a theory, which is the standard model, that describes at the current level of the experimental precisions and at the energies that we have reached so far, all the measurements, all the phenomena that we have studied, essentially. And it is the best tested theory of nature at a fundamental level. But still, there are many very basic questions that you know. What determines the observed pattern of masses and quarks and leptons? Why are they arranged in generations? And why three? And in the standard model, the only interaction that distinguishes the three flavors is the interaction of the matter fields with the Higgs boson, the so-called Yukawa interaction. And the complex phases that are present in the Yukawa couplings are also the only source of CP violation. And we know that CP violation is required, is one of the conditions that is required to explain the matter-antimatter asymmetry in the universe. So, are there other sources of flavor and CP symmetry breaking besides the standard model Yukawa coupling? And to be able to answer these questions is likely to shed light on physics beyond the standard model. And flavor physics may actually provide the first such indications of physics at energy scales that are not directly accessible to direct searches. And as I said, the CP violation is connected to a very deep and fundamental question, which is the matter-antimatter asymmetry of the universe. So where did all antimatter go? And what led to the disappearance of antimatter, assuming an initial symmetric state? We know that there are antiprotons in cosmic rays, which are consistent with secondaries due to the interactions of cosmic ray protons in the interstellar medium. We know that we can produce antimatter in accelerators. We do that all the time. But apparently there is no antimatter around us. And this looks really, really strange. So where did it go? Why is the universe 100% matter asymmetric? And can the standard model explain the baryum asymmetry of the universe? The answer is no, because the CP violation in the standard model is too small to explain it by several orders of magnitude. So CP violation beyond the standard model must exist. And where might we find it? In the quark sector, as deviations from the CKM predictions. And this is the subject of the next lecture by Neville. And or in the lepton sector, as CP violation in neutrino oscillations, or as in other new physics, because almost all TV scale new physics contains new sources of CP violation, and precision measurements of flavor observables are generally sensitive to additions to the standard model. So, but let me go to the main subject of my talk, which is rare B decays, which is another deeply connected to flavor. And in a nutshell, what are we looking for? Well, in the standard model, processes that involve flavor changes between two up-type quarks, UCT, or between two down-type quarks, DSP, are forbidden at the tree level. It can only occur at loop level through penguins and boxes. And so this type of transitions are rare with branching fractions between 10 to the minus 6 and 10 to the minus 10 typically. And what makes it interesting is that a new particle, which is too heavy to be produced at the LHC, can still give sizable effects when exchanged in a loop, as illustrated in these examples. And so the strategy is to use well-predicted observables to look for deviations. And this is an approach which is completely different from that of Atlas and CMS. It is a complementary approach. So to look for the presence of new physics through deviations with respect to precise calculated observables, rare decays observables. And so this is a way of opening a window of new physics at high scales. And in fact, the energy reach of various indirect precision tests of physics beyond the standard model is very impressive compared to the reach of direct searches, as illustrated in this graph produced by Matt Rees. So you see here the scale which is accessible to EDM experiments or to mu to E gamma, mu to E decays, or two experiments which have to do with flavor, with mixing in flavors. And you see that you can really have access to quite high scales. But let's take a plane and let's fly to Geneva. Let's forget about the pandemic and let's go to the LHC, and which is drawn in this sketch. Lhcb is located at point 8 near the airport that you see there. Here is the lake, and let's go down the cavern, and this is what you would have seen until not too long ago. This is an image of the detector as we knew it. The collision point is here, somewhere here. And this is a photoshopped image of the collaboration, which includes about 1,000 authors from over 100 institutes and from 19 countries, and with almost 600 publications, some of them with a very high impact. And the main focus is on heavy quark flavor, but actually there is plenty of other physics in the forward direction besides rare decays, which is the subject of my talk. So if you look now at the detector with a sketch superimposed, you see that here you have the collision point. So you have a forward detector with a succession of elements and dipole magnets and rich for particle ID and a very precise vertex locator to do the physics that we want to do. And here is another sketch. So at this point, the collision takes place here. Forward acceptance, I have already said. Efficient trigger for hadronic and leptonic modes, and acceptance down to very low PT, and precision tracking and verticing with a vertex locator that reaches less than 1 centimeter from the beam. So it's very, very close to the beam. And so one initial question is, why does Lhcb look so different? Well, and you see here a sketch in which Lhcb is superimposed to one of the end caps of CMS. And the reason is that beam mesons formed by the colliding proton beams and the particle they decay into stay close to the line of the beam pipe, and this is reflected in the design of the detector. And another essential point for B physics is that if you plug in the numbers, you see that B mesons typically travel a distance of the order of 1 centimeter that you can detect with our precise tracking detectors and with a vertex locator. And therefore, the idea is to look for displaced vertices and or tracks with large impact parameter. Now, the running conditions are very different from what is done by Atlas and CMS, because Lhcb is designed to run at a much lower luminosity. And the mean number of interactions per bunch crossing is designed to be 1, at least this was the case in run 1 and 2. And why is that? It's because if you want to reconstruct all these vertices, you cannot have multiple collisions on top of each other. You cannot have high pileup. Moreover, tracking and particle identifications are sensitive to pileup, and you want to avoid that. And so, as a result, while Lhcb in run 1 connected total inverse luminosity of 9 inverse femtobar, if you compare that to Atlas and CMS that collected 140 inverse femtobar, you see that there is a huge difference. And here is a sketch of the peak luminosity. So you see here Atlas and CMS, and you see here Lhcb on a log scale. How do you reduce the luminosity? Well, to reduce the luminosity, you displace the beam. So essentially, instead of having a collision head-on, you move the beams a little bit, slightly, to operate instead of the nominal 10 to the 34 of Atlas and CMS to 4 10 to the 32 per centimeter square per second, which is going to increase by a factor of 5 in run 3, so with the upgraded detector. Still, this gives us a huge production, heavy quark production cross-section, and with some 10 to the 11 decays per femtobar in the acceptance, and the cross-section for C production is 20 times larger, so you have 10 to the 12 C decays per inverse femtobar per femtobar in the acceptance. So you have a massive amount of data to deal with. So to summarize what I've just said, for Lhcb, more data is more important than higher energy. While for direct searches at Atlas and CMS, you need more energy to be able to go above, threshold production of new particles. In the case of indirect searches, where you're looking for precision, you gain from an increased luminosity, from increased production rates. However, digesting all these data is a true challenge, and at 13 TeV and the luminosity of 210 to the 33, which is what we're going to have for run 3, so for the Lhcb upgrade, you have a signal of the order of 1 megahertz in your detector. So it's a massive amount of data, and in which the more interesting B100 decays occur with a probability of 10 to the minus 5 or lower. And so this is a huge experimental challenge which requires a very powerful trigger. And let me show you the schedule. Maybe you have seen it already in the Atlas and CMS talks, but here is the data collected in run 1 and run 2. We are now at the end of the long shutdown 2, in which we are upgrading our detector to increase the luminosity by a factor of 5. Then we will start run 3 in March of 2022. And in LS3, this is when Atlas and CMS will have their phase 2 upgrades, and where Lhcb plans to have some incremental improvements to the upgraded detector. And with the upgraded detector, the objective is to collect an integrated luminosity of 50 inverse femtobar. And then there are ideas for an Lhcb upgrade phase 2 to be able to continue to run during the high luminosity phase of the LHC. The upgraded detector is, in reality, essentially a new detector, because less than 10% of all the channels will be kept, and there will be many, many changes. For example, in the Velo, we will go from strips to pixels to be able to increase the granularity, and then the trigger will be drastically changed to be able to swallow all this massive amount of data, and there will be many other changes to the tracking system, to the photo detectors of the riches, etc. So it is really a new detector. And the installation is being completed under a very tight time scale, and under very harsh conditions because of limitations to travel, because of distances, and it was really complicated. Still, it is progressing. So one last thing that was installed was the beam pipe, for example, that you see here. And so we hope to be ready in time, but it's going to be hard and tight. So I talked about the trigger and the difficulties, and as a matter of fact, run 2 served as a demonstrator for the upgraded detector, in the sense the 2 key components of the upgrade selection were already deployed in run 2. We have an alignment and calibration which is performed in real time. This allows us to produce online data which have the same quality as you would normally do offline. And this gains one step, of course, it gains money, it gains time. And the other thing, we have developed a so-called turbo stream to be able to deal with reduced data format on which we perform the analysis directly. And so the performance of a final analysis event reconstruction in real time is crucial to be able to process large quantities of data. In addition, we have at the moment a so-called L0 hardware trigger, which is going to be removed completely. And we will read the full event at the LEC bench crossing rate of 30 megahertz and implement the trigger purely in software. This is an extremely interesting development, and we will run this high-level trigger on GPUs. And this triggerless readout will allow us to have 2 times higher efficiency for hadronic decays at 5 times the integrated luminosity, 5 times the pileup, etc. But let me move to the physics results, and in particular, let's start with leptonic decays. One of the milestones of the flavor program is the B into mu decay, which is very suppressed in the standard model. It theoretically is very clean, has a branching ratio which is extremely small. So for the B sub S of the order of 10 to the minus 9, and for the B into mu, it's 20 times less, something of the order of 10 to the minus 10. It is sensitive to new physics because a large class of new physics theories had foreseen an increase to this branching ratio, and it has a very clean experimental signature, 2 mu's in the final state. And so it has been looked for by all experiments, starting from Clio in the 80s, and all these are limited to the B to mu branching fraction until the first evidence for the decay of the BS into mu was published by Lhcb, and then the first observation of this decay resulted from a combined analysis of CMS and Lhcb data. And the latest LHC combination, which is not new, shows this is shown here in this graph that illustrates the B into mu versus the BS into mu. You see here the standard model prediction, and you see that the B sub S is slightly lower. It's 2 sigma lower, the standard model prediction, while the B to mu, the central value seems to be in line with the standard model prediction. And so you see that here the era of precision measurements of the B into mu has really started. However, there is a more recent Lhcb result, in fact, a brand new Lhcb result, based on the full statistics on 9 inverse femtobar. This is the mass plot distribution, invariant mass distribution. You see a nice peak for the BS into mu, which is now has an evidence, a significance of 10 sigma, while there is no evidence yet for the B into mu, which would have to appear here somewhere. And the result is dominated by the statistical uncertainty. And so by accumulating more data, the precision will continue to increase. And this is an illustration, again, of the B to mu versus BS to mu that shows the standard model prediction and the central value of the Lhcb measurement, which is there. This is really like measuring a branching ratio of 10 to the minus 9 is really like finding a needle in a haystack. And you see here a plot of dimuon events in Lhcb. You see this very nice peak, and the opposite sign dimuons and same sign dimuons. And what you're looking for is something there with, with such level of branching fraction. So it is really an experimental challenge in which you must, understand your background and your detector extremely well. And but there are other observables that you can also measure in your B to mu final state. For example, you can measure the so-called effective BS lifetime, which is experimentally, you measure the expectation value of your untagged time-dependent rate. And I don't go through the definition, it doesn't really matter, but in alternatives model, you could have this observable is an independent way of checking new physics beyond the standard model, and this was indeed measured by Lhcb, and it's found to be consistent with the standard model at the 2 sigma level. And then you can look at other decay modes. For example, you can look at the B into E plus E minus, and this is a branching threshold that is even smaller due to the tiny ME square factor that appears in the expression, and it was considered to be out of reach from the experimental point of view, and so there was very little attention dedicated to that, and there was a limit from CDF from 2009. But there are models in which, for example, by Fleischer et al., in which this branching fraction can be enhanced, and so it has recently been studied by Lhcb, and you know, a very significant increase to the limit has been measured. But we can look at other B2S LL transition, and in particular, one can look at decay of the type B into H mu plus mu minus, in which H can be a K or a K star and a 5. So it's the same loop diagrams, but different spectator quarks, and that you have in for these different final states with a K or a K star or a 5, for example. And for these decays, you can have rates, angular distributions, and asymmetries are sensitive to new physics. They can be sensitive to new physics, and a lot of phenomenological work has been invested in defining observables that are clean from a theoretical point of view. Clean in the sense of being free from form factors and leading orders. And however, this is really debated, and not everybody agrees on how clean these observables are. And so the first such decay is the decay of the B into K star, which goes into K plus pi minus mu plus mu minus, and you can perform an angular analysis of this decay. You have the angles of your K star and mu plus mu minus system. You have 3 angles, and you can define observables. And in general, good agreement with the standard model has been found in most observables. But then Lhcb observed a tension in a very counterintuitive observable, which is called P5 prime, which is constructed from ratios of angular observables to be robust from form factor uncertainties. And Lhcb measure, you know, some excess with respect to the standard model prediction in two Q-square bins. However, this is quite inconclusive when you add the Atlas CMS and Bell data. But then there has recently been an update based on almost 4 inverse femtobar, therefore doubling the number of B zeros to about 5,000 events. And you see here illustrations of some of the observables and with the standard model prediction. And you see here the current result on this P5 prime variable, and the local tension in these 2 bins is confirmed. And the global analysis of all these observables finds a deviation of the level of 3 sigma, slightly in excess of 3 sigma, consistent with previous results. But there is a new analysis in which one looks at the charge B in K star plus mu minus, and Lhcb performed a full measurement of a full set of angular observable for this decay based on the full statistics. It is more difficult experimentally, so there is a smaller signal yield, and therefore it is to gain sensitivity. One uses a folding techniques in which some observables are in fact eliminated, and one can and then one can play this trick and perform the measurement. So you see here the peak with a 9 inverse femtobar of the B plus, and you see here the P5 prime observable. Okay, this is the plot, and no particular comment, but okay, the tendency is there in those 2 bins. And then similarly, one can also perform an angular analysis in the B0S into phi mu mu final state. which has just been updated. So this is a paper which is currently on the archive with 4 times more B sub S candidates. In this case, the final state, K plus K minus, or from the phi decay, mu plus mu minus, is not flavor specific, which means that you cannot know what was, you cannot distinguish between the B0 and the B0 bar from the final state. And the results in this case are compatible with the standard model predictions. And here are some illustrations of the various observables. There is also an intriguing set of results in differential branching fractions, always for the B to S to mu mu transitions. And in general, for all these various final states, data tend to be lower than the theory prediction at low Q squared. So, for example, you see here in the B sub S into phi mu mu, this is quite clear. However, the comparison is limited by the theoretical knowledge of the form factors. And this is, in fact, this result here is, in fact, brand new. And you see here the effect that I was talking about, and it is 3.6 sigma below the standard model in the Q square region between 1 and 6. Okay, but let me go to a subject which is cleaner from a theoretical point of view, which has to do with always with the same transitions, but with tests of lepton flavor universality in these transitions. So, lepton flavor universality, of course, is the property that the 3 charged leptons, E mu tau, couple in a universal way to the standard model gauge boson. So this is a boring property. And in the standard model, the only flavor non-universal terms are the 3 lepton masses that scales with these ratios. However, if the new physics couples in a non-universal way to the 3 lepton families, then we could discover it by comparing classes of rare decays which involve different lepton pairs, for example, E over mu or mu over tau. And we can test that again in B2S L plus L minus transitions, that is to say, in flavor changing neutral currents with amplitude evolving loop diagrams that are suppressed and where new physics can be at the same level as the standard model. And actually, the standard model quantum numbers of the 3 families could be an accidental low energy property, and the different families may well have a very different behavior at high energies, which is signaled by their different masses. And if new physics couples in a non-universal way to the 3 lepton families, so this is just a repetition of what I just said. And yeah, I had the same slide twice. I'm sorry about that. And then we can look at the family of R ratios, and we compare the rates of B to H E plus E minus, a B to H mu plus mu minus, where B can be a B plus or a B0 or a B sub S or a lambda C, a lambda B, and H can be a K plus or a K star 0 or a PK system or a phi. And we can construct these ratios, RH defined here, integrated the rate in Q square from a certain Q square min to a certain Q square max. And these ratios are clean probes of new physics. And the theoretical uncertainties on these quantities is small, and RH in the standard model is 1, neglecting effects due to lepton masses, with QD corrections and at the percent level. This is a very challenging experimental measurement because lepton identification is anything but universal. Electrons emit a large amount of bremsstrahlung, degrading momentum and mass resolution. And you have different situations depending on whether, you know, this bremsstrahlung was emitted upstream of the magnet or downstream of the magnet. And you can try to recover the photons that you are lost to have some sort of bremsstrahlung recovery. But that doesn't capture all cases, and some of these photons that you try to associate to the calorimeter clusters are misattributed, and so you have a pure, the mass resolution is not of the same quality for electrons and for muons. And also you have a lower efficiency of the electron trigger. And this is shown in this plot. If you look at the invariant mass of K plus mu minus, for example, and K plus E plus E minus from this recent paper, you see that there is a very big difference in the two mass distributions, and there is background which is specific to the E plus E minus channel. Note that the scale is not the same. Here we are at 5200, which is here, and so in the case of the electrons, you have a partially reconstructive background in which you lose a pion, and then you have a longer radiative tail. You have leakage from this decay, so it's simply not as good. Then, how do you address this experimental difficulty? You address it by measuring this R ratio as a double ratio. So to mitigate the muon and electron reconstruction differences, you perform a measurement as a double ratio in which you normalize to the resonant control modes. So instead of measuring directly B to H mu mu divided B to H over B to H E, you normalize each of these two decays by the corresponding resonant control mode. And in this, if you perform a measurement like that, you have big cancellations. So the relevant experimental quantities are the yields in the four modes and the trigger reconstruction and selection efficiencies for the four modes. You introduce a new element which is called R small J psi, which is the ratio of this quantity that you have, you are normalizing to the resonant mode. But this is known to be compatible with the unit within 0.4%, and you expect no new physics to appear here. And if you have the double ratio, the similarities between the experimental efficiency of the non-resonant and the resonant modes ensure a substantial reduction of the systematic uncertainties in the double ratio. So you have big cancellations, and instead of having to know the efficiency of the muon channel with respect to the electron channel, you need to know the efficiency of the muon channel with respect to the resonant muon channel, and similarly for the electron, which is experimentally much simpler. And the analysis is, of course, performed blind, not to bias the result. And there is a new measurement of RK, which is now on the archive, based on the full Lhcb statistics, based on twice as many Bs and in the previous analysis. So, so the measurement is a measurement of the RK defines the case in which you look at the B plus into K plus E plus E minus and mu plus mu minus. And there are important cross-checks to this measurement to make sure that, that we are doing things correctly. So you can measure the ratio of the resonant modes, the R small r J psi. In this case, you have no cancellation of the efficiencies. You must know the efficiencies in an absolute way. And this turns out to be compatible with 1 very nicely, and is a which I just said, resonant electron and mu modes, if you want. And this is also being checked as a function of various kinematic variables, and to be flat and consistent with unity. Or you can also measure the same ratio for the psi to S, for example, and again you find something which is compatible with unity. And this is the result of the new RK. You see the result and 6. So this is the new Lhcb measurement. This is a measurement from to unity. And you see here the same plot as a function of Q squared. So this is the Lhcb measurement, and here are the other results from Babar and Bell. The evidence is another measurement of the RK star, the so-called RK star. And the measurement in that case was performed in Q squared bins. And you see here the unity line, which is here. And you see that even in this case, you are below the unity line, and the effect is of the level of between 2.2 and 2.5 sigma, based on a partial statistical sample, because this only comprises 3 inverse femtobars. So this is the new result that we are eagerly waiting for. And but there is another puzzling result. There are no update transitions. And in this case, one studies lepton flavor universality ratio of the. This is an entirely different class of decays, because we are talking about 3-level charge current with Lhcb suppression. They are not particularly rare. They are at the so you have to control an overwhelming background. They're sensitive to any new physics model which couples preferentially to third generation leptons, and this is the theoretical prediction for these decays at the 1% level. It has been studied. I mean, this class of decays have been studied by Bell, Babar, and Lhcb. And here you have the current result, the current combination from the flavor averaging working group. It dates from spring 2019 because it has not been updated. So you see RD star on the vertical axis and RD on the horizontal axis, and you see here the combination of the various results, Bell, Babar, and Lhcb. And all the experiments see an excess with respect to the standard model prediction, and there is a tension at the level of 3.1 sigma from the standard model, which is mainly due to RD star, 2.5 sigma on RD star. And this is, of course, a very intriguing thing, because it occurs at the 3-level standard model processes. And here are the source of the data. You see here for RD star, for example, the theoretical prediction, and you see here the experimental points that lie all about the standard model prediction. Okay. A final word on lepton flavor violation. Many models that are proposed to explain these tensions naturally allow for lepton flavor violation processes with rates that are experimentally accessible. So one should also look for those. And in fact, this is done. And there are so there are several limits by many experiments, and here are some limits from Lhcb, both on neutral decays and on charge decays, so at various levels of precisions. So one should certainly continue to look for direct lepton flavor violation in such decays. So my take-home message is as following. Precise measurement of flavor observables provide a powerful way to probe for new physics effects beyond the standard model, complementing direct searches for new physics. And this is particularly relevant in the absence of direct collider production of new particles. So it's one of the best things that we can do at the moment. We produced many world record results, and for some topics we have moved from exploration to precision measurements. Most of these results show good compatibility with the standard model, but hints of lepton flavor universality violation are still persisting. And this has generated a lot of interesting theoretical ideas, and I think you have had an example of that in the talk by Nazila a couple of days ago. But we need more data to test these hints, and the full analysis of brand 2 is very well advanced, and results on a new analysis that looks at RK and RK star together should appear hopefully soon. And but also results from Atlas and CMS would be very welcome in this domain. And I would like to publicize an Atlas, CMS, and Lhcb flavor anomaly workshop that will take place virtually at CERN on the 20th of October with a community of theorists and community of experimentalists in which we look at the flavor anomalies, what one can do at high PT, what one did at the Lhcb, and what one can do in the future. While we are waiting for the high precision results from the Lhcb upgrade and also from Bell 2, of course. Thank you. Yeah, there.
We have
There.
yes. We have time for a few questions. Yes. Oh, I'm sorry. We can start. Okay. Then.
Hello, very nice talk. I have a question concerning this B2D tau decay. Is it possible to infer some information about the tau polarization in this decay?
You're talking about B2D tau, the lepton flavor violation. I don't know. If I don't think that was the purpose of that analysis. I mean, that analysis was done to put a limit on lepton flavor violation decays.
Because the polarization of the tau gives you some additional handle on it.
Well, I would have to look it up.
Yes, I'm sorry.
Could you go to page 48? I didn't understand something there. It's 48.
48.
Yeah. Yes. The little lepton message. Corrections at the
Percent level.
corrections to the ratio, to the R?
To the R. Yes.
But the charges are the same, so why
For the electron mode or the POD corrections are evaluated at that percentage level.
Okay, but the masses are masses. It's not corrections. Masses are kinematical effects, not.
They don't cancel out.
Okay. Next question.
I think he has a comment. Yeah.
I have a question. I think it was when you were talking about B2S lepton pair. You mentioned this discrepancy between the observation and the standard model prediction, but I noticed that on the plot there was also a curve from lattice calculations, which agreed with the data, I think, much better. Can you comment on that? It was earlier, I think. It was. Oh yeah, this one. Yeah, this one when you.
Which
next slide when it's yeah, okay, here there is a lattice curve, I think, going through the points. No, the lowest one. Yeah, and it goes.
Yeah. Well.
Or maybe I saw it. It's hard to see here.
I think these deviations should be taken with a grain of salt, because indeed they depend on which theory you take as your reference, which is debatable. You can make a choice or alternative choices. So I do not intend to make a a big thing out of that. These are tendencies that one has, that one sees.
Okay. One last question from Paul.
Thank you for the very, very nice talk, Monica. I have, forgive my ignorance because I'm a theorist, but I'm trying to understand these detectors for other reasons. So let's suppose that the standard model is correct and there's no new physics. And we look at this R sub k, which is a beautiful variable, very clean. My understanding is the electrons agree and the muons, there are too few. So my question is, as an experimentalist, do you have any suspicion why some of the mu plus mu minus events are not picked up?
Obviously not, because all the systematics effects that we have been able to control, the results are what I'm showing to you. If we knew anything more, I wouldn't be showing you. I wouldn't be showing you these results. So, can there be hypothetical systematics effects that we are neglecting? This you can always ask. This is always possible that we are overlooking something. This nobody will be able to exclude maybe the combination of some minor systematics and some statistical fluctuation. This you cannot exclude. But while, for example, in the case of three-level decays, you really, this is systematic, the experimental measurement is very difficult, and you must know your simulation, all the decays that enter, all your backgrounds, you must control them very, very well. In the case of this double ratio, this is an extremely solid measurement from an experimental point of view. And the fact that small r, so the ratio of the two resonant modes, turns out to be 1 as a function of your kinematic variables, this is very solid from an experimental point of view. So, of course, you cannot exclude, maybe there is something that has not been completely understood, and at the same time, there is a statistical fluctuation in your data. This is always possible. However, as I was trying to say, we also have an alternative analysis of the same decay, of of RK. So we just published RK on the total sample on the 9 inverse femtobar, but there is a new analysis which is looking on RK star and RK with a different method, always using the same detector, obviously. So if you have a problem at the level of the reconstruction, but okay.
I think it's a good conversation for the coffee break. Okay.
Very short. In Professor Durouk's lecture on the first day, he mentioned that CMS might measure R sub k.
Well, we're looking forward to that.
I'm sure you are.
Okay.
Is there any? Will they compete with you in spectroscopy?
I don't know. This you should ask Professor Derek, who is not in the room, I think. Yeah.
Okay.
Oh, go ahead.
But I don't think so. But they have a lot of data. You have a lot of data.
So me personally, I'm from Atlas, and we're trying to do the Atlas star measurement. Both Atlas and CMS have started to take data with this in 2018, so our sample is not as big. We might be comparable with 1-1 on RK star with Lhcb. Has to be seen, right? But it is more like a proof of principle for 1-3. So there will be better measurements with 1-3, and so yeah.
CMS has parked a lot of data, so they took a lot of data with a particular dedicated trigger that they have parked, and they did not analyze it immediately, and I think that they're now doing that, and so we're eagerly waiting for those results and to see what they have. It will be very interesting. Yes.
There's also a question.
I'm sorry. Okay. Madam Quiroz, do you have a question still?
Yeah, hi, Monica. I just wanted to ask you, can you measure taus and compare taus with muons or electrons as you did with muons with respect to electrons?
Well, tau with muons we are comparing in RD and RD star.
I was thinking on RK. Oh, well, yeah, okay, no. Okay, I understand.
It's more complicated,
Yeah,
and
yeah.
I'm not sure whether there is any analysis on that at the moment.
Okay. Okay, this should be interesting just to check the
Yeah.
non-universality just with the third generation of leptons. Yeah. Okay, thank you.
Two taus. Yeah, that's right. You have two taus. You're right.
Okay.
Yeah. You have two taus. So two taus is indeed because in RD and RD star you have one tau.
So my comment is actually prompted by your question. You see, there is one way of So there's one possible way of escaping this double ratio test. And I would like to draw your attention to something that was very surprising to me, which probably has no application for this beautiful analysis, but we have discovered very recently that all the standard programs in high energy physics like Jean, they have a wrong treatment of the masses of the muons. When you are in the regime in which you convert photons with Q square, which is quite larger with respect to the mass square of the muon, in such a case, you would expect that the mass terms, which have the electron masses or the mass of the muon, would be correct. And we noticed that, for example, Jean is totally wrong. They didn't put, you see, the right matrix element with the proper treatment of the masses, which is more important, closer to the, you see, the Q square of the order of 2 mu square, but it is persistent up to large energies of these photons. You see, I don't know if this has any, I'm just telling you that the recent test of existing tools, like for example, Jean, shows that, you see, there is a problem in this place, and this kind of problem would escape your test of double ratio.
Okay, but we have so many measurements. I mean, Lhcb has performed so many measurements that to have a problem precisely there. Okay.
Okay.
Okay, but thank you.
Let us thank again, Monica. So we are going to continue with the talk by Neville Anu on a review of CP evaluation spectroscopy measurements of Lhcb.
Good. So is the microphone working okay?
Should be, yeah.
1, 2, 1, 2. A little closer.
So I'll give you the 10-minute sign. That is the 10 minutes. I'll warn you when you have.
Are you giving me 40 plus 5?
Yes, 40 plus 5.
Okay, good.
Yes.
Well, that's good. So thank you again to the organizers for inviting me back here. It's a wonderful place to be giving a talk, and like everybody else, it's the first time out of the UK for, well, 18 months. So it's great to be back in Corfu. And so I will talk about CP violation and spectroscopy measurements at Lhcb. So it's following on from Monica's talk on rare decays. So I'll give a general introduction about what I'm going to be talking about. I will update on new Unitarity Triangle measurements, in particular the angle gamma. I'll talk about CP violation and mixing in charm. All these are new results. I'll talk about new measurements in spectroscopy, and I can actually skip this, or at least shorten this, because Monica touched on the upgraded detector. So just by way of introduction, I assume everybody is familiar with the Unitarity Triangle. This was the status in 1995. This was before Barbar and Bell started up. Very little was known. There were measurements from Lhcb and from Na48. Then Bell and Barbar started up, and of course the picture of the CKM matrix improved considerably, and sin 2 beta was very well measured, and the other parameters of the CKM of the Unitarity Triangle were also measured better, but not with great precision. So now we come to the present time. This is summer 19, and the Lhcb then makes these measurements, and the triangle, of course, is significantly better defined, but yet with certain parameters that are still rather poorly measured, and the angle gamma, this angle here, being one in particular. Right, so I'll start with mixing and CP violation in beauty and charm. Now, I'll start off with B and BS mixing measurements at Lhcb. Now we know that the neutral Bs mix through this box diagram. So a B will transform will be produced as a B, will mix to a B bar at decay. And this can be measured by a simple asymmetry where a B at production is tagged as a B, and then observed decay as a B. And you can subtract those number of events from the case where you have a B produced, and then it decays as a B bar. All right, and you can, by flavor specific mode, you can tell whether it's decayed. So this is a relatively old result. In fact, I think I've presented it here before. This is mixing in the B0 system, and you see this beautiful distribution. It's not new. This is something that was very well measured already by Barbar and Bell. But nevertheless, Lhcb have the best measurement of the B0 mixing frequency. Here you can see the Bs transforming to a B bar and back. Now, this measurement is new. This is in the B0 system. This is in the BS system now. This I think is probably my favorite plot in particle physics to date. This is the BS mixing, and because the mixing frequency of the BS is so much higher than the mixing frequency of the B0, you see these beautiful oscillations And this is just the B0 being produced, and as a function of time, it is oscillating. It is changing its state. And so this is just the asymmetry as I described before. And the mixing frequency has been measured to the world's most precise. Good. So that's new in B mixing. I come now to the measurement of the unitarity triangle angle gamma. This angle that is poorly measured. Now, I must stress that all these measurements, the vast majority of unitarity triangle measurements are actually in loop diagrams. They're not measured in tree, they're measured in loops. So in principle, loops, you could expect new physics contributions to manifest themselves in loops rather than trees. And if you plot the unitarity triangle measurements just in trees, you get this. It's not a triangle at all. It's the very few. There's this ratio VUB over VCB, which is a tree measurement from B to U decays, and there's the angle gamma. All right, so gamma is predominantly measured in tree diagrams, in tree processes, and like all the other parameters. So it's really important to constrain this angle gamma, because this is, if you like, a standard model process. Assuming no significant new physics is appearing tree decays, it's a standard model benchmark. Okay. So what we're saying is that, new physics is maybe appearing here because everything's in loops, but this is your standard model benchmark. So you want this one to agree. And as such, it's a theoretically clean measurement. So how well do you determine gamma? Well, this is the current, this was our summer 2019, before the new results I'm about to present. The errors are something like 5 to 6 degrees on the angle gamma. Right. If, however, you take all other measurements of the unitarity triangle except the angle gamma and calculate what gamma is from the lengths, from the angles, and from the sides, you get this, right? So the angle gamma measured from loop processes, according to all the measurements you can make of the triangle, is much more, assuming of course it's a triangle, is much more precise than the measurement you can make. So this is the motivation for measuring gamma for as well as you can, and in particular getting into this sort of precision, and we're far from it. Right. So the first the measurement I'm going to explain is a charge B decaying to D0K, because this channel is actually the channel with the most precise measurement at present. The charged B decay mode. So this is an example of, just to give a feeling of why you actually, how you make this measurement. You have a B minus here. Okay, of course, charge, the B plus is implied as well, but this example is a B minus. So a B minus will decay to a D0, which in this case into D0 K minus by a favored mode, a CKM favored mode, and then it can decay into this final state K plus pi via a Cabibbo suppressed mode. So you have a B minus going to K minus K plus pi minus via a D0 decay. But you have another path to this same decay mode, decaying via a suppressed mode here, a Cabibbo suppressed mode to a D0 bar, and then going to the D0 bar then goes via Cabibbo favored mode to give the same final state as this process here. All right, so the branching fractions for these modes are the order of 10 to the minus 4. Okay, so that's just for the favored decay mode. But the point is, these, because one's favored, one's suppressed, the two decay paths actually are not so different in their rates. Okay, which makes for a precise measurement of gamma. The point is, those two decay paths interfere with each other, which gives you the handle on the measurement of gamma. Right, so it's interference between those two paths. So this, again, I think is a beautiful plot. This is showing direct CP violation. This is a sample of B plus and B minus going to K plus, K minus. K minus, this is the mode I showed before, you can see the direct CP violation. This is the rate of B minus, and that is the rate of B plus. You see a huge difference in those rates, and this is, of course, a measurement of CP violation. B minuses are decaying very differently from B plus. So one looks at the asymmetry of this mode minus this mode. It's basically just a counting experiment, and you can extract gamma from these relative rates. And so that was just an illustration. Lhcb have done a recent combination and measured these are the charged B modes where the Ds are going to a whole variety of final states. There are also there are B plus and minus modes, there are B0 modes. For charm, there are various modes here that are investigating CP violation in charm. So there are a whole load, and there are also BS modes in the combination. So here we go. So here is the new average. So this is combining all those modes I just showed you. The new error is 65.4 plus 3.8 minus 4.2 to be compared with just to remind you, I showed you before. So, okay, we've improved the statistics a little bit. We are still quite a way away from the indirect constraint. So just to remind you, Barbar and Bell closed with these precisions. So the Lhcb measurement of gamma now is completely dominating the world average. And so you see, as I say the charged B modes are actually dominating the combination. Here in green is the combination. There is the charged B modes, the neutral B modes here, the BS modes, which is a time-dependent measurement, is here. So clearly the errors on the neutral and the BS modes are not competing with the B plus and minus modes. Okay, but new results on these modes are yet to come. This is consistent within, I think, 2 sigma of the combination. Right. So here is the evolution of gamma as a function of time, and you can see there's a constant improvement. But we won't see any further major improvement, of course, until we upgrade the detector. I'll come to at the end. So all I've talked about so far is this triangle here, which we call the Unitarity Triangle. All right, and lambda, which is sine of the Kuiper angle, each of the sides of the unitarity triangle is of the same order in lambda. So it makes for a nice triangle with measurable angles. There is also what we call the BS triangle or beta S triangle. And here we're dealing with the elements of U and D quarks. Here we replace the U and Ds with the strange and the charm. So this is a second unitarity triangle. However, this is so-called beta S here. And here, though, we have two sides which are of order lambda squared and one side of lambda to the fourth. So this angle beta S is very small. Right. Now we come to the third triangle, which I call is in the charm system. So here we're replacing the angle, the elements with the charm quark. Okay, the charm quark here. And so this is what I call the B triangle, and this is why CP violation in the charm system is so difficult to measure, because we have two sides of the triangle which are of the order lambda, and the third side is the order lambda to the fifth. So we have, we're measuring CP, or the angle, the CP angle, if you like, is of the order of lambda to the fourth. So we're talking, 10 to the minus 4 level for CP violation in the charm system. So I'm going to quickly talk about measurements on this triangle and on that triangle. So so first of all, the phi s. Now phi s is just actually minus 2 beta s by definition. Beta s is this angle here that I talked about there. Right. So the most straightforward way to measure phi s is in bs to j psi phi decays. And I won't talk about the method, but essentially it's not identical to the time-dependent asymmetries that you measure for the angle beta. You measure a time-dependent asymmetry in BS and BS bar decays. The difference being we're dealing with vector particles. But the angle beta in the unitarity triangle, it's j psi k short. Here we're doing j psi phi. But phi is a vector particle, so one has to do an angular analysis of the decay of the phi decay, separating in CP even, CP odd modes. But I haven't got time to go into that. This phi s is expected to be very small, and it's quite precisely predicted. So I will just say there, this actually isn't a new Lhcb measurement. It was 2019, but one does a simultaneous fit of the width difference phi s with the gamma s with the phi s phase. And here is the CP violating phase as measured by Lhcb, and combined and showing with the standard model prediction, it is spot on. I mean, this is Lhcb modes combined. There are a number of different modes. But what is new are measurements from other experiments, and the new world average for phi s is minus 0.050 plus or minus 0.019 radian, to be compared with the standard model prediction. You see we're way off, actually coming close to the error on the standard model. So it's totally in agreement, and we're way off the standard model prediction. So it's way off the standard model error. So we have a long way to go to improve that precision. So CP violation in charm. Now these results are new, but I'm going to start off with an old result just to remind you. Lhcb discovered to 5 sigma significant CP violation in charge round about 2 years ago. So I'm going to just recap that result. So direct CP violation in charm, we're looking for a decay of a D0 to some final state, which has a different amplitude to D0 bar decaying to the anti-state, if you like. All right, so we're looking for differences exactly as I showed you before. We're in the B system, we're looking for differences in the charm system. So we're looking for an asymmetry of D to a final state F in respect to D bar to the final state F bar. And of course, the most promising channels are those Cabebo suppressed decays, where the CP violation arises between tree and penguin amplitudes, as I mentioned before. So, and again, this CP violation in charm is predicted to be very small, the order of 10 to the -4. So these results, I think I even showed before at the last Corfu meeting. The thing is, you've got to get a clean sample of D0s and D0 bars, and you get those from observing D stars to decay, where the flavor of the D is then tagged by the soft pion from the D star decay. Similarly, you can tag the flavor of the D0 decay via semi-leptonic decays. Okay, so you produce D0s, D0 bars in very large numbers. You look then for differences in the decay rates between the D0 and the D0 bars. Right, but the trouble is, experimentally, that's an easy measurement to make. It's just, it's just event counting. However, it's actually significantly more difficult because you've got differences in the production rate of Ds and D0 bars. Now that seems counterintuitive, but I can explain it if you like. It's the fact that we have a proton-proton machine, so we don't have a symmetric starting point. So there's a small production asymmetry in Ds and D bars. So we have to correct for that. The production asymmetry is much bigger than the effect we're trying to measure. But also there are small experimental differences, albeit small, the percent level on the performance of the detector for both positive and negative charges. Right, so we have to, any detector asymmetry for plus or minus charges, we have to correct. So the way it's done is we take 2 final state modes, K plus K minus and pi plus pi minus, and we subtract the 2 asymmetries. And in that way, because the production asymmetry and the detector asymmetry are common for both modes, that those asymmetries cancel in the difference. All right, so we measure delta ACP, which is the difference in the asymmetry of K plus K minus and pi plus pi minus. Okay, so, right, so all I can say is the samples are incredibly clean, right? Here is D0 pi plus, D0, this is prompt events into K plus K minus, pi plus pi minus. These are the semi-leptonic modes. They aren't quite as clean as the prompt mode, but the measurement of the delta ACP, i.e. just the difference of the rates, normalized difference of the rates, is 15.4 times 10 to the -4, which is a 5.3 sigma measurement. So that was the discovery of CP violation in charm for the first time. Right, so since then, there are various other measurements that have been made. So D0 to K short, where here the D0, K plus, K minus is a control channel. The CP asymmetry is measured to be that. There is no, consistent with no CP violation. The precision is a factor of, worse than a factor of 10 from the delta ACP measurement. So it's maybe not expected, but it's improved the world's precision. There's also been measurements in all these other channels here, again, improving the precision, but all at the percent level. So it's all compatible with no CP violation, which is maybe to be expected, right? So more data is needed, but note that Lhcb is now actually utilizing these neutral modes for the measurements. Now, this is a rather complicated analysis, and it actually took a whole seminar to describe it. So I will only really just outline the technique. This is measuring the D0 mixing parameters, and it's measuring the mixing parameters in D0 to K short, pi plus, pi minus. Now, this is maybe sort of counterintuitive. I showed you before the D, well, I showed you B mixing, but one can do a similar analysis with just counting flavor-specific modes as for the B, but it turns out the most accurate measurement is from this mode using a Darlitz plot technique. Now, okay, so we have two mass eigenstates, the heavy and light D mesons, and of course these are a linear combination. There's P and Q, they're normalized to 1. P squared plus Q squared is 1. P over Q can be imaginary, which gives rise to CP violation. The difference in the mass eigenstates, the difference in masses, M1 minus M2, is X normalized to the width. The difference in the widths is Y, and the phase of P over Q or Q over P is just phi. So you have handles to all these parameters in this Darlitz plot. And so 30 million D0s into this decay mode have been recorded. And again, use this technique of D star to D pi to tag whether you've got a D or a D bar. Right. So the method, you produce a Darlitz plot of K short, pi plus. So you have M squared minus versus M squared plus, where M squared plus is the K short pi plus or minus combinations for either D0 or D0 bar. And this, it turns out this part of the plot is weighted by wrong sign decays, and this part is right sign decays. Sorry, the WS is wrong sign, RS is right sign. This is dominated by Cabebo favored decays. That's dominated by Cabebo disfavored decays. All right, so there is a difference in the mixing parameters over the plot. So what you do is you use a bin flip method where you divide this Darlitz space into bins, and they're really weird shaped bins. These bins are from Clio C and Best 3 are known to have equal or close to equal strong phase differences over that region of the bin. All right. So then you take this bin, you divide it in the middle. It should, so one should have symmetry here, and you take the difference of the symmetric bins. All right, and if you do that, here is the asymmetry from the various bins, and you see these strange shapes. They're not strange. They are showing mixing of the D0 to D0 bar. And if you have no mixing, this would be a straight line. So you see in all these different Dalitz bins, you see all these structures. They are different because it's strong phase dependent. And here are the measurements, X and Y. Here is the mass difference between the eigenstates. And this is quite mind-boggling. M1 minus M2 is 6.4 times 10 to the minus 6 electron volts, which is, for publicity purposes, 1 times 10 to the minus 38 grams, which I think is impressive. This is the best measurement. It's 7 standard deviations. It's actually the first significant measurement of the mass difference. Okay. Delta Y, this is a measurement of indirect CP violation. One's looking at the asymmetry individually of D0 to K plus K minus decays as a function of time. And one is looking to see, so this is the asymmetry between D0 and D0 bar decays. And one sees a time dependence in the asymmetry. And given a time dependence in the asymmetry, one measures the slope. And this is related to the, I think, by sine phi, the phase of indirect CP violation in the D system. And of course, it is compatible with 0 within 2 sigma. So one needs more data before one says one's measured indirect CP violation. So I'm going to quickly go through, changing the topic now. I'm going to talk about exotic spectroscopy. And this is a really nice plot. This is new hadron discoveries at the Lhc. All right, and as a function of time. So this is totally new hadron discoveries, baryons, mesons. And, you know, every time you see a dot here, this is a tetraquark, that's a pentaquark, etc. Okay, and it's been an impressive line of discovery over the years, and over 60 new particles. And here they are, but this time it's, so apologies to CMS and Atlas colleagues. This is new hadron discoveries at Lhcb. That's new hadron discoveries at the Lhc. So we now have 55 of those 60 or so were Lhcb. And here are the tetraquarks and the pentaquarks there. Actually, Atlas and CMS got, there are a few up here, including pairs of B quarks that are new from Atlas and CMS. So, pentaquark discovery. So this was already now 5 years ago or more, where the first observation of these pentaquark states were seen. I just flip back just to say, you know, the baryon is 3 quarks, the meson is quark antiquark, the tetraquark is a 4 quark state, QQ bar, and the pentaquark is a 5 quark state. So Lhcb discovered the pentaquark in the K minus, in the J psi P spectrum in lambda B to J psi P K minus decays. So here is the bound state of the so-called PC, which decays to J psi P. And after a few more years, this is now coming to 2019, it was actually found that one of the pentaquarks actually was 2 pentaquarks. This was after more data. And here is the 4312. And here we have the established pentaquark states. Now, the thing is, what are these things? Are they really bound states of quarks? Or are they like a molecule, sort of deuterium-like, with a quark, a baryon with a meson, which are forming a molecular state? Or are they some sort of complicated rescattering process of which I'm not quite sure? But the point is that these new states are actually rather close to the mass thresholds. Here, this is sigma c d0 bar. This pentaquark is rather close to the mass threshold there, just below it, right? So it sort of points that it could be a molecular state where you have two, bound state of a sigma plus with a d0 bar. Similarly here, this is close to that threshold. I don't think that one is. So the time, more work needed. Well, there's been more evidence since then. This is all new. This is in the same mode, but it's in a different B decay. This is a J-psi proton final state again. And okay, here we have another state observed in both the proton and antiproton final state with a mass 4337 with a width of 29. There's also been a pentaquark evidence for a pentaquark state 4459. Here, this is very new in J-psi. What's this symbol called? God, lambda. In J-psi lambda. So here we have another state. So this one is this is a CC bar UUD. This is a CC bar UDS. So we are actually beginning to see various flavors of new pentaquark. Right, so that's pentaquarks. What about tetraquarks? This is hot off the press. This is sort of an interesting one. This is the first doubly charmed tetraquark observed. It's called the TCC plus, and it was seen in the mass spectrum of D0 pi plus. Okay, so the conjecture is that this could be. It is quite close to the mass threshold of D star plus D0. All right, so the conjecture is this could be a molecule of a D0 and a D star. Okay, or of course it could be a complete bound state. I mean, the jury's still out. It's 273 away from the threshold. So this is a nice resonance. It's 10 sigma. It's manifestly exotic. And for not wanting to turn this into some sort of stamp collecting talk, there's also new observations of tetraquarks. There's a CC bar US and a ZCS 4000, 4220 in this spectrum. This is J-psi K plus. J-psi phi, there are states 4630 and 4685. Both are significant, 5.5 sigma and 15 sigma. So the zoo of these pentaquark states and tetraquark states is now growing, and but I think the jury is still out what they actually are, or whether they're a combination of different things. But they're certainly bound states. Right, so I think I can skip this because Monica said this already. I was just going to say for the future, no sooner do you build an experiment, but you have to prepare for the next one. We've virtually got a new experiment starting within the next well, within the next year, but hopefully within the next 6 to 8 months, let's say. And then we prepare for high luminosity running. Monica went over the new detector. She also went over some nice pictures of the construction, which is what I do in my day job. I work on this, which I'd love to tell you about, but no time. I told you that we already were at sub 5 degrees for the measurement of gamma. We expect to get, after upgrade 1, which we're preparing now, to 1 degree. This is the detector beyond 2030, which also Monica talked about, where we hope the CKM matrix we can get to this. So I apologize for slightly running over time. The summary, if I may just summarize that we've recorded 9 inverse femtobarns of data. New physics is becoming constrained within the Unitarity Triangle measurements, but still a way to go on gamma. Fantastic platform for spectroscopy measurements. And these weren't really in Lhcb's original physics portfolio. There's still much room for new physics, higher precision required. So we are all working hard towards this new detector where we can increase our statistics at least by between factor of 5 and 10 in the coming years. Okay. Thank you.
Now we have time for a few questions. First on the floor. Yes, Franco.
Due to the fact that the proton-proton has a different production of the 0 and the bar 0, you are obliged to make the difference and not give the singular asymmetry in neutral to 0. So you may make progress on that, or to find the individual asymmetry, what should open more in Bell too, because it's a plus and minus, and so it's not disappearing.
Yeah, I mean, that's right. I mean, I think, I'm not absolutely an expert on this, but I think the asymmetries for the K plus, K minus, pi plus, pi minus are predicted to be in opposite directions, and they're about the same order, right? So now, yes, and I showed you D0 to K plus, K minus for the indirect CP violation measurement. So we have made the measurement of K plus, K minus, and pi plus, pi minus individually. To give you an idea, the errors, I think, are about a factor of 5 times higher on the individual measurements. So, yeah, we can actually, with more data, I'm sure we can get down to the CP violation in those individual channels with more data. But we have to work on systematics. But with more data, we measure the production asymmetries better and better. You know, the errors come down. So I think we will definitely measure the individual asymmetries. Yeah, eventually, maybe in a couple of years' time, we'll have a more precise measurement of that.
Some other floor questions? I don't see. Are there any Zoom questions? No? So I just want to make a comment. This is incredible, you know, your results. We have measured, as you know, there are 4 independent angles that can be measured in the triangle, in the first 3 lines of a CKM matrix, which is beta, gamma, phi s, and then the last one is a very small one over the 4. So we still have not measured that according to you, but we are approaching that. That's incredible. Because that's the order lambda 4 angle, which is in general it is independent, you know.
It's
they are all related within the standard model, but in principle, for getting unitarity, they are a remarkable result. Okay.
Thank you.
If there are no Zoom questions, no other floor questions, let us thank again. Beautiful talk. I'm very happy to introduce now Ivo Vazielas, another component of the Portuguese army that is present here. And he's talking about multiple modular symmetries as the origin of flavor.
All right, thank you for the nice introduction, and thank you also to the organizers for the opportunity to give this presential talk. And I'm looking forward to the excursion tomorrow as well. Good point. Yes. All right. So I'm going to talk about modular symmetries, and I recommend, let me get this out of the way. And I recommend this paper by Ferruccio Ferruglio that is over there in the archive. It's also published. And the idea is that we're considering this field, complex field tau, which is called the modulus. And this field takes values in the complex plane, but only in the upper half. And we're considering eventually not this gamma bar symmetry, but we'll start with it first. And this gamma bar symmetry has elements which I'll generically call gamma, which send this modulus to gamma tau given by these four integers a, b, c, and d. And it's usually more convenient to represent these elements in a 2x2 form, but be careful, don't just multiply them like a matrix because the transformation is this one. But still we represent them in a 2x2 form, and the constraint is just that these four a, b, c, and d are integers, and the determinant of this matrix is 1. This group, well, when we discuss groups, we usually don't want to consider all of the elements, particularly when the group is infinite. Rather, we want to discuss the generators, because if you know the generators, you know everything. And this group has two generators. One is called S tau, and the other one is called T tau. And the S tau is just the element that will put a minus sign and invert the tau. Remember, this tau is a complex number. Whereas the T tau is just something which just shifts the real parts of the modulus field by plus 1. So in the notation above, this would be the 2x2 matrices S tau and T tau here. And with these two, you can generate by composing the elements, all of the elements of the group with group multiplication. Now I'm going to very shortly consider another group, which is this gamma bar open brackets n group here. And this is basically just a subgroup of the other one, where you just consider integers which are multiples of this capital N. So the A is just 1 plus some integer multiple of capital N, the B the same thing, and the B is just integer multiple of the capital N, and the C the same. So when you actually consider this subgroup of the other group, it's not just a subgroup, but an invariant subgroup, and you can construct the so-called factor group. And this one is the one I will actually be dealing with. It's called gamma sub n. And the interesting thing is that this gamma sub n, for at least small n, is isomorphic to well-known groups, which are often used as flavor symmetries as well. The S3, the group of permutations of 3 objects, A4, S4, and A5 for the n equals 2, 3, 4, and 5 respectively, as shown over there. For those of you who don't remember very well your group theory, in very bad handwriting, I will just give you a very, very quick recall of what it means to be a factor group with the example as S3. So you take a group G, I'm going to use as example S3, and this has some elements, and I can make, with the invariant subgroup, which is in this case called H, I'm going to make cosets. So the first coset is a subset of the group, which has just the elements of G, which are the elements also of H, the subgroup. And then I'm making a different coset, which is just the other elements which are left over, multiplied throughout all of the elements. So let's say I take S3, which has these 6 elements in permutation notation. And the invariant subgroup of S3 is this Z3, which just has these 3 elements: the identity, the cyclic permutation 1 to 3, and its square, the 3 to 1. So I left over the 2 cycles. They're not part of the invariant subgroup. When I take the factor group, actually, I take as elements of the factor group the H itself and one of the 2 cycles multiplied by H. And that factor group in this case is just isomorphic to Z2 because it just has 2 elements, and that's the only group with 2 elements. Z2 is everywhere. Anyway, let's skip this group theoretical bit. So I want to consider a theory which is invariant under this gamma sub n, and this is embedded in supersymmetry. So I'm considering as my building blocks chiral superfields phi. How do they transform under this under the action of these gamma elements? The phis themselves are function of the modulus, and when I shift the modulus by action of the gamma, then the field phi actually picks up this prefactor here with some power here, which is called the modular weight. So this is just as I choose the representation of the chiral superfield under the group, I also choose its modular weight, and it appears in its transformation under gamma, and it gets multiplied by this, which is the matrix representation associated with the element gamma. So let's say that I'm considering an S3 invariant gamma 2, which is isomorphic to S3. Then I want to choose if my field phi, my chiral superfield phi, transforms as a singlet of S2 or as a doublet of S2, of S3. And then if it's, for example, a doublet, then it has 2 components, and this will be a 2x2 matrix corresponding to the correct element gamma. And this will be maybe clearer in a future slide, where I'll do an example with S4 actually. Then I write my SUSY action, and it's just as possibly well known to you. And it will have the Kähler potential and the superpotential. I will focus more on the superpotential here. In fact, I will not discuss the Kähler again. And basically, the rules for making the invariant superpotential are just the usual ones. I need to make all of the, and this is a maybe complicated expression, but it's just a complicated way of saying a simple thing. I just want to have all of my singlets that I can build as polynomials of my different chiral superfields, phi1, phi I1, phi A, and etc., multiplied by some coefficients. And then I sum over all of these invariants, and that's the most general invariant superpotential. Of course, superpotential is holomorphic, so I only have the phi's, I don't have the phi stars. And these coefficients, which are called here the y, why did I call it that, are interesting because the coefficients themselves transform actually very similar to the transformation of the chiral superfields when acted by gamma. So the coefficients y, capital Y, are themselves function of the tau, and when the tau is transformed by the element gamma, then the y's go pick up a prefactor also with some modular weight. Notice just that here there's a minus sign on the chiral superfield, and then there's a plus sign here on the so-called modular forms. These coefficients are called modular forms. They themselves can be representations of the non-trivial representations of the gamma sub n group, and this is the transformation. So the modular forms themselves, which are the coefficients, they're no longer just complex numbers as you have in a, shall we say, in a regular flavor symmetry. But if you're using as flavor symmetry, a modular symmetry, then they themselves transform in general like this. Now I'm going to shift a little bit, and I'm going to talk about stabilizers of these modular symmetries. What this means is the special values of the tau. So I have my modulus tau, and I want to find special taus that when I act with some specific gamma transformation, this brings me back to the same tau. So this will happen for a specific tau for a specific element of the group. And if I do that, and I look at one of the previous equations for the transformations of the chiral superfields under the action of gamma, I will find that I can, because there was a gamma acting on tau, but then if that gamma acting on tau gives me back the tau, then I get this kind of equation, which is just the representation matrix acting on the y, which in general is a multiplet, is giving me back, I said that it's a transformation for the chiral superfield, but it was a transformation for the modular form, sorry, the y, not the phi. Gives me back just the prefactor multiplying by the same y without the gamma because of this. So this is just applying for stabilizers. And then I look at this equation, which is equation 31, because I just grabbed it from a paper. And then I see it's kind of like an eigenvector eigenvalue equation. And we just conclude that for stabilizers, we can predict the direction of the modular form because it's just one of the eigenvectors of the row matrix. So this makes stabilizers particularly interesting also because given that if I am in that special value of the modulus, I'm preserving, for the case where this prefactor is 1, I'm preserving that element as a residual symmetry that was not broken by the modulus getting that specific VEV as a stabilizer. So then with Miguel, which is sitting there, and with Yeling, which at the time was a postdoc in Southampton, we went to do kind of systematic search for all of the stabilizers of the smaller gamma subbands up to n equals 5. There's also a paper which we refer to in that paper by Steve King and Guijun Ding, which have done, which have found several of these stabilizers that I will show. Just to very quickly clarify the idea of these stabilizers, I will give a couple of examples which are n independent, so this works for any of the n's. So you remember that my S tau generator just sends the tau to 1 over minus tau. So one of the stabilizers for this particular element is just I, because if I act on I with S tau, then I get minus 1 over I, which is I. So that stabilizer does not depend on n. Another stabilizer that doesn't depend on n is if I choose as tau the imaginary infinity I infinity, and I act on it with t tau. Oops. I'm in Greece. Then my t tau acting on I infinity just adds 1 to it, a real 1. So I just throw that out and it stabilizes it. But usually stabilizers depend on n, and I will show this in a few, not slides because I'm just scrolling, but after I scroll a little bit. The method we use to find systematically the stabilizers, first, the stabilizers are usually, when you draw the domain for these gamma subbands, it looks kind of like this for S3. And the stabilizers are found in the vertices of this, in the vertices or intersections of these subdomains inside of the full domain. For example, here at the middle, I have the stabilizer, which is n independent, one which is just I. And I want to find, for example, I want to know what element is stabilized by gamma, by tau prime there. So what I can do is I find a transformation that takes me from tau prime to tau, or from tau to tau prime. It's a group, so they will always be there, and it's the inverse. I already know what stabilizes here, so I just know that if I go here, I'm stable here and go back. I went back to the tau prime again. So that combination, doing the three things one after the other, is going to stabilize tau prime. So that's just what's written here. But you get the idea, and if you don't, you can ask me at the end of the talk. So here again, I'm showing you the domain a little bit more colored now, although you barely see it over there. It's a beige color instead of gray. Here is the domain of gamma sub 2, which is isomorphic to S3 again. And here is the list of the stabilizers. You see here the ones that are n independent, I and I infinity for S tau and T tau respectively. S3, of course, is a not so big group, so there's not that many elements here. They're arranged by conjugacy classes, the conjugacy class 2 and 3. And here is the respective stabilizers for the respective elements of the group. Now the same thing, but for A4, or gamma sub 3, it's isomorphic. And here the domain, of course, is bigger because as you might understand, now when I do the modulus 2 or the modulus 3, I can shift with t tau more times before I get back to the fundamental domain. So it shouldn't be surprising that the domain for gamma 2 is shall we say, narrower than the domain for gamma 3, and this of course continues. Also, instead of the 6 elements of gamma sub 2, I now have 12 elements. Taking away the identity is just 11 ones, which are here on this table. So I have here again, we can see here the T tau with its usual stabilizer, the S tau with its usual stabilizer, but a few more stabilizers in the, which you can see more or less as these white dots marked in the fundamental domain, and in the table the corresponding elements that are stabilized. So let's say that I'm doing an A4 model with one of these modular symmetries, and I want, as a residual subgroup, so that I can do my usual model building, I want S tau as a residual subgroup that I didn't break. I could just assume that I get as a VEV for the tau either I or 3/2 plus I over 2, which should be, let's say, right about this one. Right? Or just this one, if you prefer. I think I got the correct one. Anyway. Now, I want to discuss not just using one of these groups as flavor symmetry, but more than one. So that's the title of my talk. And there will be a talk later today by João Penedo, which I'm trying to find somewhere over there. So when that my colleague and friend from CFP gives the talk later in the afternoon, I hope that you're here. I think you will discuss the more traditional way to do it, which just with a single one. So it's based on these two papers, one with Steve and Yeling, and a more recent one with the master students from Lisbon, João Lourenço, not Penedo. he's a postdoc. And the idea is that basically I want to have multiple modular symmetries because I want to use multiple stabilizers. That's why I spent time mentioning stabilizers. So this is again the most complicated general way of doing a simple thing. The idea is that if you have multiple modular symmetries, when you write the superpotential, you just have to write the most general invariant under all of the symmetries. And I can write it in this complicated way. And then, of course, my chiral superfields and my modular forms are going to transform under the multiple modular symmetries. But the idea is exactly the same. So I'll actually just skip to this example with S4, which was used in that paper with Steve King. And here, finally, I show you what a row looks like for one of these particular elements of, in this case, S4. In the often used Altair-Ferruglio basis, where the T generator is diagonal, but the S generator is not diagonal. So let's not confuse the notation where I show you the gamma element as an element which is a 2x2 matrix like this one, the modular symmetry, and the representation of a particular triplet of that same modular symmetry for the same element. All right. So this is the row that appears when I say that I transform a chiral superfield or a modular form, and that's the row that appears in equations like this, which appeared before. And you remember the few scrolls ago, I was saying that for a stabilizer, I can predict the shape of the modular form because it's an eigenvector of the row. So I know that this is the row that I want. What would be a shape of a modular form with this particular stabilizer which preserves the S? Then I use this matrix, row I of S, which is this one that I wrote here, and I find an eigenvector, and one of the eigenvectors is this, which you can check or ask me about it. But if you can see that the three, well, it works out. It's one of the eigenvectors. Let's not do eigenvector diagonalizations in real time during my talk. So then, actually, I wanted to have three modular symmetries in this case, all of them isomorphic to S4, because I want three stabilizers, tau A, tau B, and tau C. And then I want to arrange it in such a way that these three symmetries are broken to diagonal subgroups so that at the lower energy scale, it's just a single S4. And then I can proceed to build my usual models, more or less like João Penedo will show later, but with an explanation for why I'm using also not just one single modulus field, but three with different stabilizers. Then some details of the actual model are here with the different representations chosen for each of the three S4s, A, B, and C. There's, for example, the left-handed lepton field is a triplet just under this one. The neutrino, the right-handed neutrinos are singlets. There's these special fields which break the thing, and the modular forms, because now we need also to choose the representations for the modular forms, are here. For example, there's a triplet under the first one, this one is a triplet under the second one, and so on. And there's these special fields which we use precisely to do this, shall we say, trick of breaking the multiple S4s to a single one. So these fields are actually triplets under two of them, so that when I give a special VEV to this phi AC and phi BC, I can actually break correctly to the diagonal subgroup, where the leftover is that the multiple modular symmetries, which could have different elements at each time, are going to have just the same element at the same time, so that I can pretend that I only have one single S4 at the end. The invariant superpotential is written here. I don't expect you to parse that in real time. And here is the specific VEV that I want for phi AC and phi BC, so that I actually do break to the diagonal subgroup. And we are not just assuming this VEV to be the one we want this, but we have a superpotential that aligns it in this direction. And then basically, so we go from this expression where the three S4s are apparent. After plugging in the VEV that I want that gives to the diagonal subgroup, I get to this expression where it looks like there's only a single S4, but I have as a residual memory the special modular forms aligned in the special directions which are associated to each of the stabilizers. So this is why I went to all the trouble of putting the multiple modular forms, is just so that I can get to the end, to the multiple modular symmetry, so that I can get to the end and have a justification, a good justification for the special directions that I want, so that I can then use these special directions to predict mixing angles and so on. And that's then the usual model building. From this direction, YA, for example, I get a matrix with this kind of structure. It's very rigid structure. From the other one, which looks like this, I get this rigid structure where you see the entries inside are correlated. It's because of that special direction and so on and so forth. So then you diagonalize the PMNS matrix that you get, and it looks like this. It has one fixed column and the other two depend on this remaining free angle. And it's called the trimaximal one type mixing, and it gives a good fit to the mixing angle. So I kind of went fast through this usual model building part, and if you have questions about it, we can discuss at coffee break, because my point here was just to present this idea of the multiple modular symmetries, and the bottom line is that I want to use them so that I can have access to multiple stabilizers as a, shall we say, as a very good justification for the special directions of flavor breaking. So my conclusions now, I think, how am I with time? So we can maybe go a little bit earlier, like by 1 minute to coffee. So my conclusions is that modular symmetries are a promising framework for trying to explain the origin of flavor. And in this, the so-called stabilizers play a key role. And I like stabilizers so much that I went to the trouble of doing this framework where I have more than one modular symmetries, just so that I have multiple stabilizers, and then from that the special direction. So that's basically what I wanted to tell you today. Thank you for your attention.
Thank you for keeping the time. Okay, now we have time for a few questions. Yes.
There's one behind you as
we
well.
can.
Yes, I thought that you wouldn't see it.
No, I think the symmetries become less and less promising now. Essentially, you are doing symmetry building instead of model building. So my question is, you can reproduce everything like here with just usual Flavon fields, and you are fighting for just correct alignment. And actually what you have shown, these essentially web alignments is like 1, 0, 1. It's easy to obtain with just usual potential. So now what is advantage?
So I hope that João will talk more about usual advantage of modular symmetries as opposed to non-modular symmetries as flavor symmetry. The thing that I actually didn't discuss in the talk is that when you use modular symmetries, also you get rigid structures and usually predict relationships between the masses, which is not usually the case in the traditional flavor symmetry. You can also do sometimes, but it's not as direct to get.
Any other question in the floor? I'm sorry.
Yeah, just maybe it's a trivial question, but the fact that from these experiments we see that the third generation, that the generations are actually, there is no universality, right, in the standard model. So we are, experimentally, we are seeing these changes. Now, does this picture say something about it or not?
Just to be sure, you're talking about the Lhcb anomaly?
There is anomaly cancellation in the standard model is just, perpendicular, right? I mean, it doesn't go through intergenerationally. So what we are seeing now in the standard model from these experiments on the two-flavor variation is that.
Yes, okay.
About it, right?
So, no, in fact, it was very nice to hear the previous two talks. I'm very excited with these anomalies. In this particular work, we didn't do it. I have, although I don't want to give a new talk now because we want to have coffee, but I have some works where we use flavor symmetries. They don't need to be the modular type, but they can actually explain some things about that. But the type of work that I've done is in the context of also having leptoquarks. So let's say you have a leptoquark, and then you have not just Yukawa couplings with the Higgs, but you also have the Yukawa couplings with the leptoquark. Let's say it's a scalar leptoquark. But that structure is also has its own flavor structure. It's not just one coupling, but in general a 3x3 structure. And what you can do also with the flavor symmetries is much like you arrange the structure of the Yukawa couplings with the Higgs, you can also arrange the Yukawa couplings with respect to the leptoquark. And you can very nicely explain, for example, why you have a leptoquark that couples just to muons. And if you do that, then you have one very good solution to why are the flavor anomalies being seen. Because you have an effect just in muons and not in electrons, even though you have a leptoquark which would in principle also couple to electrons. Why not? And the why not in that case would be because of the flavor symmetry. And in this type of symmetries that I mentioned, like A4 and S4, in fact, maybe I'll even just scroll. One of my special directions is precisely this direction, which has just one non-zero entry, this what I call Y electron, Y muon, and so on. And with this kind of special direction, it's very easy to just say, okay, my leptoquark just couples to muons, for example. And this is already like an element that we already had before the anomalies. We already had this kind of special directions and used them to explain the PMNS matrix, why the PMNS matrix has columns that look more or less like this, for example. Mm-hmm. And you can also apply it to leptoquark models.
May I just to make another, just one thing. I mean,
okay, you should read it.
Okay,
I will be there. I will be there.
I think it's next question. Next question.
It's a very good, interesting idea.
Thank you.
Right, it's good to have alternative ways to look at things. So I like to see how much, that's exactly my curiosity as well, you had to implement a superpotential, try to descend all the symmetry from a Keller potential. Is an R symmetry at the very end hidden in these constructions, or why you need that? I mean,
why do I need a Keller potential, or
why you need to descend from a supersymmetric construction? I mean, usually the other approaches, which Alexei talked about.
Yeah. So it's even in, shall we say, regular flavor symmetries, we usually use a supersymmetric framework, and it's precisely related with the Vev alignment as well. It's not strictly necessary, but it controls that the Vev alignments are the way you want and not too perturbed. But in this particular case, because we are using modular symmetries and we have the modulus tau, even sometimes it's string inspired. superstring inspired.
Oh, okay.
So we're already naturally pushed towards supersymmetry,
So
which
an extra ingredient as well.
yeah,
Okay.
it's semi-hidden in my talk because I was doing superpotentials.
Okay. I see a question by Jean.
Thank you.
Just a brief comment about, I mean, in this setup, SUSY also plays an important role to get something predictive, because if you don't have holomorphicity, you can put a lot of things in your superpotential as coefficients. So this really is, unfortunately, sure.
It's true, but for example, if we're discussing the Vev alignment, and this is for scalars, right? And in the scalar potential, it's very hard because you'll have like the phi and the phi dagger. So there's no normal symmetry that you can put because you try to put some U1 to prevent this phi from touching that other phi. But then you have, or this phi with this chi or whatever. And then you have phi star, chi star, and there's a quartic term which you cannot stop, and they touch each other. And when they touch each other, the directions that you want and were beautiful, then they get mixed. That's true as well. And then you'll get corrections also to that.
Okay. This
Do you have any parameter you prefer? You would prefer some experimental results? Any experiment?
So in this kind, not just the particular framework that I'm discussing with multiple modular symmetries or even with modular symmetries, but usually the kind of, so we have the post-dictions, which is getting the mixing angles, but these are already observed, so it's kind of cheating. We have hopes that we get a good value for delta, which hasn't measured yet, and then when it's measured, it will help our model instead of killing our model. But usually the type of predictions that we have that are not yet observed and we're always looking forward to is, for example, lepton flavor violating stuff. Because we're dealing with flavor and we are adding extra ingredients, so often there will be contributions to stuff like mu3 gamma, very often. So that's usually the most likely place to find some kind of confirmation to this. And like in the previous talks we're mentioning, we basically are looking at flavor. So this kind of flavor anomalies, as in fact Claudio asked about, is also very promising because even though it's not strictly just on the Yukawa couplings of the standard model, but other extensions which are not flavor symmetries, like leptoquarks, also could be supersymmetry if it was still fashionable, they bring their own type of flavor problem because of the extra states associated either with supersymmetry or the extra couplings with the leptoquarks. And then you can also apply the same symmetries that you applied to solve the standard model flavor problem to the beyond standard model that you want flavor problem. And then you can see if the predictions that are coming from the solution to this side, you make prediction on the other side and then you go loop. So for example, this kind of flavor anomalies from the Lhcb is exactly the type of thing that you'd expect if you have leptoquarks and the same type of flavor symmetry.
Okay. I don't see any other question. Is there any other one? No, I don't think in Zoom either. So I can ask a very short, challenging question because I promised Steve that I would ask one.
I have your
it's a question that some people have already asked, but I mean, I will repeat it because it's a very important one. You know, these schemes, in order to have predictability, they have to be based on supersymmetry, right? Is there any hope of using some of the interesting novel features that you have without being attached to SUSY? Because as you know, whether we like or not, SUSY seems that nature, at least so far, you know, does not need SUSY for anything.
At least low energy one, right?
Yeah, low energy one. Yes, I mean we should always.
So and if it's not,
I'm not excluding. But I don't believe in the theorem that anything that is not supersymmetric is nonsense. That is very extreme.
So that,
not having any religion either in favor or against SUSY.
There are certainly non-supersymmetric flavor models around. Usually, so the price is that sometimes you lose a little bit of predictivity. We do what we can. I mean, sometimes also we predict too much, right? Back before Diabase measured theta 1,3, many flavor models, including the ones I was working on, were predicting theta 1,3 to be 0 or very small.
Right,
And then, of
right.
course, all of those were killed.
Right.
But you could also say, okay, then instead of doing a supersymmetric version of this model, which predicts theta 1,3 to be very small, I make a non-supersymmetric version where I don't let me use that as an advantage.
Okay.
So this is the game that model builders play.
Okay. I think it's the right time to break for coffee now. Okay, let us thank you again. And we should be back in how many?